Thanks for attending this session. If you were in the keynote this morning, I wasn't expecting it, but Jim kind of covered the why of, we are having this session this afternoon, which is really AI infrastructure management. Open source software is really now very much the way that AI providers out there are actually delivering access to costly resources, which are the GPU. We are going to try to give you an idea of a playbook on how, as a service provider, you should actually approach this question. So I'm Vincent. I'm the Chief Technology Officer for Red Hat in Asia Pacific, normally based in Singapore, but I do travel quite a bit. And I've got a number of functions as well across the open source community, which includes a role with the Green Software Foundation on a Green AI committee. And I'm also a technical oversight committee member of Finos. I have with me Daniel. Daniel, you want to give a quick word?
Sure. Is mic is something weird? By the way, hi, I'm Daniel. I'm from Boston. We're working from Red Hat, by the way, and I'm basically DevRel advocate, but not only taking care of Java, but also any kind of developer. Even if you are a Linux developer or a YAML developer, I don't care. So we can talk together. And I'm a huge contributor back to the CNCF as like a technical advisory group or DevX, like a developer experience. If you're any interested in developer experience contribution back to CNCF, and please let me know. I'm a co-chair and a long-time ambassador and Java champion. So if you actually want to reach out to me, you can Google me. So you can Google Daniel O, and then you can reach out to me, have any question. Let's go.
Thank you, Daniel. So the way we are going to do this is I'm going to cover the different platform layer, really covering infrastructure, data plane, all the way to how you optimize AI application. And then Daniel will take this into an actual blueprint, kind of give you an idea of the state-of-the-art AI inference optimization, how it runs today, and we'll do a quick demo as well. So let's start with the economic imperative. I'm sure all of you know there's a lot of investment going into AI infrastructure. I think it's estimated to be about 1.5 trillion US dollar that is going into building AI data center. That's a lot of money. But then at all level, if you look at even a simple GPU like a H200, will probably cost you $30,000 just to get one of these. So that's a pretty big investment. And then when you add the data center cost, the energy cost, right? Like those GPU need a lot of energy. Those are actually very costly resources. The moment you rack a GPU into your data center, irrespective of where you are running AI or not, you're actually paying something. So that's really a problem. Now, if we look at the industry itself, there's a lot of evidence that suggests that GPU are heavily underutilized. This is one of these evidence actually come from weight and biases. They basically, publish these studies and show that in the data that they have, which is essentially the consumption on the cloud services that they can look at as an enterprise, they are seeing around 15% utilization of the GPU, which is pretty poor. So if you are a service provider, or even if you are an enterprise and you basically make this CapEx investment, you have a big issue to solve. So the way we look at this from an economic point of view is really as progressing the stack. Today, a lot of services, they are what we call infrastructure as a service. They give access to GPU, where the economic model is charging for the GPU per hour. And in that model, the only thing you can do is maximize the hardware utilization. We'll see later, there are some techniques to do that. But it's very hard to actually make a good margin just by renting GPU. So once you start to go up the stack, if you look at it from a platform as a service perspective, now what you're actually providing is more of an access to the model. And then your metric is very different. You are starting to charge per token or per job if you are doing training. And that's a lot more interesting. That gives you an ability to build your stack in a smarter manner to maximize the efficiency of the stack itself. If with the same GPU you can produce more token, then your margin actually goes up, right? Pretty mathematical, pretty simple. And then of course the highest, we've seen probably OpenAI now start to go into this business as well, is actually the software as a service side of the business. If I provide you with an AI-enabled app, I can make all these optimization up to the application layer to make sure that you minimize the consumption of token. So we'll see a bit what are some of the open source components to achieve this, starting with the infrastructure foundation. So the infrastructure foundation, no surprise, the past 2 years or so, Kubernetes has established itself as the main project for providers who are doing orchestration at scale of GPU. That is the de facto standard today. It went very fast. I still knew providers that 2-3 years ago, they were only doing Slurm-based orchestration for GPU. I think the industry has totally moved away from this to really use Kubernetes. Now, why? Obviously, Kubernetes gives you out of the box this ability to manage multi-tenanting, which is super important if, as a provider, enterprise, you'll have many teams who need to access those GPUs, so you need to share them. And if you are obviously a cloud provider, then that's pretty much your economic model, is to have different customers consume your GPU at different time of the day or for different purpose. Now, the problem we had with Kubernetes is what I call here the trap of legacy allocation. If you look at 1.5 to 2 years ago, the traditional device plugin model that we use in Kubernetes was very ineffective to do resource allocation. Why? Because with a device plugin model, you basically don't make a difference between a 800 or 800 GPU. You don't know how much memory they have, and certainly how much memory is available for specific workload. So you are doing blind allocation of workload to the GPU. That's a big problem. So the first solutions that we had were, of course, to have smart scheduler. Smart scheduler at the Kubernetes level to do intelligent bin packing, and then increasingly cloud-native scheduler. Q is an example of such project where Q essentially provides complex policy management for certain allocation requirements like gang scheduling. So you need to do distributed training at scale. You need to make sure that all pods start at the same time to deliver a job, and you have enough pod to finish it. Then Q can actually solve this issue. Very good for distributed tuning type of requirement. Q also enable other kind of SLO management like fair sharing. So you can basically build SLO policy and then enable basically what is your priority workload to get access to GPU, or make sure that different tenants actually share the resources. So very, very strong capability that comes from the Cloud Native Computing Foundation. This is necessary as well to enable what I call a two-tier control plane. Is if you start to go up the stack and you need to do intelligent routing, that is the minimum capability you need in the engine to do this. We have a pretty close use case for us at Red Hat with our IBM research colleague. Internally, they use a GPU cluster called Vela. You can go to this article, it's been published this year. So the IBM research team, by using queue-based scheduling, managed to get 90% utilization for their job inside their internal cluster. So that's actually a huge achievement. Granted, they are a research organization, so they do a lot of tuning. You may actually have different type of workload. In fact, in an enterprise context, most people do more inference than they do tuning. Yeah, but it's good as a starting point. Now, one thing that is very important this year is we've gone beyond the scheduling strategy. DRA, which stands for Dynamic Resource Allocation, is now generally available since Kubernetes 1.34, and that totally changes the game because DRA helps us access the actual resource with awareness of what the GPU is, what type of memory, what type of interconnect you have at your disposal. So that's a total game changer. The way that DRA works, the approach is quite similar to a dynamic provisioning of storage. The way we used to do it, we're still doing it for Kube. If you, sorry for the picture, I'll try to cover here, but essentially in the Kubernetes scheduling here, you basically, yeah, thank you, that's awesome. So the key is really here in the Kubernetes control plane. DRA provides you essentially device class, which is like the catalog of GPU and their capability. Right? So it's to understand exactly what this GPU can do. And then it has a concept of resource slice. Resource slice is the inventory of accelerator that is now free, where you can essentially allocate workload. Then you move to resource claim. Claim is essentially the request of jobs that need to be allocated. The way we actually declare a resource claim in the array is we can use the CEL expression to basically declare a policy. So if you have minimum memory requirement or certain type of SLO, you can actually declare them in your policy. So what the array gives us, thank you, Daniel, we can go back to the bigger slide. So what the array gives us is this paradigm shift where now we can do device-aware and resource-aware allocation. We can even go beyond a simple GPU. So if you have certain NVIDIA GPU model that gives you slicing, for example, the Grace Blackwell processor, they allow you to divide a GPU in up to 7 slices, and the size of these slices can be allocated dynamically. So now you can basically start a workload or a model on a small slice and grow the slice as we go along, thanks to this dynamic resource allocation capability. So that's really a game changer. So we dealt with the infrastructure, but on top of it, I'll focus now on inference. So we estimate that in enterprise context, probably 90% and above of your cost is actually going to result from AI inference, not from tuning. Very few people do actual model training these days. Most of the use case is actually consuming the model at scale. So the open source inference engine newly incubated into PyTorch Foundation is actually VLM from our standpoint. VLM, actually, if you look it up, this year it has the highest growing number of contributors as an open source project. Pretty impressive how much usage this project has gained. VLM is a high throughput, low latency inference engine. So it really focuses on GenAI inference, nothing else. And what it addresses is the core inference challenge, which is a typical bottleneck you have in LLM. In LLM, the key bottleneck we have is kind of twofold. The first one is LLM have sequential processing. When you do decode, you've probably seen how tokens are generated. Basically, the token generation is not parallel, it's sequential. So that's bottleneck number one. Second bottleneck is the generation of token needs to have this short-term memory to actually work, and this short-term memory is actually happening in a key value cache. So the memory utilization of this cache is super important. So VLM really focus on optimizing those scarce resources with a number of techniques, including page attention, continuous batching, that we will cover next. I just want to draw your attention as well. A big role that VLM plays in the open source ecosystem is to provide open choice. Open choice of accelerator. All the key accelerator providers are upstream contributor of VLM, so they contribute plugin. So you can run VLM on NVIDIA GPU, on AMD GPU. Even recently, we actually worked with Chinese and Korean GPU provider. You will see on the market next year Japanese GPU as well. Yeah, so that kind of gives you a huge amount of choice in terms of hardware if you don't get enough access to those really hard to find NVIDIA GPU. The second thing is from a model perspective, we work with all the key model provider, open weight, open source, whatever you call them. So we are able to provide day zero access to new open model like Western model, Llama, is an example, or Eastern model like Qwen.
Yeah.
So page attention, why is this important? The challenge of page attention is very clear. If you look at how in a typical process, the LLM will generate an answer, is basically a sequential token generation. Because the size of the input to an LLM and the size of the output is not determined upfront. Typically, what the model does is it will pre-allocate kind of too much space, too much memory blocks to actually be able to generate an answer. In most cases, this means we have a very heavy fragmentation internally of the memory space to actually provide an answer. How page attention changes is it uses the concept of virtual memory the way we do it in an operating system like Linux. And it basically creates a block table. So when you are essentially generating those tokens, you are basically using this memory space and dynamically allocating the available memory in blocks to the output generation. So what page attention is doing. Now, one key aspect of that as well is if you have been working with LLM and in particular agent, there's actually a lot of the space that is repeating. So when I have a chat template in an LLM to a model, actually the chat template is passed every single time you send a request. With that memory allocation strategy, we can basically cache only once this repeating pattern. So that's a huge improvement by about 40 to 50% of the memory reutilization. That's a very important technique that VLM enabled. The second thing is continuous batching. In the past, we used very naive batching technique where essentially we would wait for all requests to finish before starting GPU pass at one go. So that is very good to get this kind of efficiency in orchestration, but that is very bad because a lot of your GPU are waiting for processing. So how VLM changed the game is by allowing continuous batching. It dynamically allocates the processing to whatever GPU a pipeline is ready as and when. So you basically have a bigger overall throughput. The last thing I want to cover is you will hear a lot about mixture of expert. What is mixture of expert and why is it important? Mixture of expert is a way in the internal model logic to make sure that you can have a huge range of weight on the model, but you only activate the models that are the weights that are necessary for a given request. Why is it interesting? That's because the computational cost of your request to the model is basically codependent to the number of weights that you activate. So by activating those weights dynamically, we usually reduce the total cost of processing. There's one slight economic drawback to this, is that because this model, they tend to have a lot of latent weight, they need a lot of memory to be allocated. How did VLM support this? VLM essentially provides what we call expert parallelism. What it means is we can use 8, 16, 64 different GPU to essentially shard the model weight. Yeah, so we get access to all the GPU memory across multiple number of GPU, and then we allocate the request to the right GPU that has the weight that needs to be activated. Yeah, so VLM manages this under the hood. All right, so we've covered VLM. That is essentially dynamically improving the efficiency of the generation of token with the same amount of GPU. The last layer is what I call the intelligence engine. We'll start on a discussion that I've been having with quite a number of firms that I meet. They tell me, Vincent, we already have an API gateway, so why don't we just put the model behind and just use our existing API gateway in front, right? Because we know an API gateway very well. This is a terrible idea if you want to manage the economics of AI. Here is some of the reason why. In terms of the primary focus of an API gateway, you are only managing RESTful traffic. This traffic is typically stateless. You don't actually, you don't know if there is an instance of a REST endpoint that is more efficient than other. In AI, this doesn't work like this. Different model or different instance of the model will have totally different usage, utilization, and efficiency based on the type of request. So you need to do dynamic routing and mapping, which is a lot more aware of your hardware level utilization and your cache. Yeah, so that's the prime reason. But beyond that, there is a lot of technique and capability we need from an AI gateway. That includes, for example, traffic unit. You need to measure even kind of token utilization because you want to be able to charge back to your customer. You need to have load balancing that is cache aware. If there is a type of request that always come in a repeated manner, you want to route the request to the same instance of model that has already served because the request answer is already cached. Yeah? So a lot of reason, but essentially we see the AI gateway as a way to dramatically reduce the cost of processing by maximizing those patterns of utilization across your AI infrastructure. So next year, I think you are going to hear a lot this term. We already start to hear a lot from a research perspective, but a lot of the enterprise I work with is starting to realize that mixture of model is a very interesting capability. You have heard this morning about Open Router. So Open Router is a project that enables mixture of model. Yeah, but actually your AI gateway can do this natively. So you don't even need to have this external router. What mixture of model is a bit different from mixture of expert. Here I'm basically routing the request outside of my model. So I have multiple model endpoints. I have models that are thinking model. I have models that are maybe smaller models that are specialized. They've been tuned for specific use case. I'm basically deciding on the fly which is the best model to serve a request. VLM provided very recently a capability called semantic routing. So this is what I'm showing here. So what semantic routing does is it has a classifier model, which is based on modern BERT. And this classifier model is essentially looking at the request in terms of categorizing it. Yeah, so it's deciding where to allocate the workload based on the type of request. This is a huge margin multiplier if you are running a platform. These are some figures out of the box, right? Without any additional tuning of the routing that we obtain. We basically get 10% additional accuracy out of the box with semantic routing while reducing the latency by 47% and reducing the number of tokens that need to be produced by 48%. That means you are getting about 2 times more juice from your GPU, yeah, just by adding this additional intelligence in your platform. So that's what I wanted to cover. And now Daniel will show you how these different pieces work together.
Sure, yeah. So before we get starting into there, so just a quick question. How many people are actually using Kubernetes today? A lot. That's great. Nice. You know, also this topic, Vincent, gives a lot of AI model, but this is not AI dev track. So this is why we're going to show this LLMD as container and cloud track. Because you saw a lot of great things from open source. Vincent talked about a lot. And how do you manage it? How do you control like a resources, GPU, et cetera, et cetera. And now you're probably thinking of the way, how do you actually put it together on your on-prem? Maybe somewhere cloud for using Kubernetes. So I got one more question. How many people are actually a developer and software engineer? Okay, that's good. Yeah, and you want to actually using AI app dev? I mean, you AI, not just chatbot, not Google Gemini, and you want to actually develop and run AI application. Oh, good. Yeah. Yeah, a few, really good. So LLMD, you probably heard about that recently. This is like a super popular, getting more. It's gives some like a distributed inference. So whenever you so just LLM or SLM, all model just binary files. If you go to Hugging Face today, there are more than 2.2 million models today. So many. And then when you pick one of them, like a Quen or a Llama, whatever you pick it up, and then you go to detail, you can find a bunch of the file, like a safe sensor and config JSON and among others. That's exactly you need to have serving runtime for like a model serving runtime, which is the inference server. And Vincent already talked about the VLLM, which is really easy to make it happen. Allocated GPU accelerator, and then run your deploy your LLM files, and also you can expose your endpoint like API for developer. So the LLMD, just imagine your enterprise environments. So back in there, you probably many microservices, doesn't matter Java, Python, or JavaScript, you have a multi-microservices to implement your business services. And now you arrived AI era, which means you have many AI services at some point in the future. Not only one chatbot. There are many AI services, generative AI, agentic AI, whatever you call that. And which means that you have a multi-inference server based on that AI services, but also you have a multi-GPU accelerators. So that's you're gonna stand up, you build your own architecture, how to make it allocate this all kind of stuff. So as you can see, running on Kubernetes, of course. So many popular company like Red Hat, IBM Research, and Google, and CoreWeave, and among others, they actually created this project and as open source. And then running on Kubernetes, and then scale your VLLM and like a inference server. And then in the end, eventually you can build your own model as a service on top of that, based on like a semantic routing and among others. So if you go to a little bit detail, like some more architecture point of view, and then there are actually 3 layers, like an intelligence layer, which is actually process your prompt. Whatever you ask, like give me some great like image or video or code generation, whatever you ask, this is like for example, like that endpoint here, like a get/completion. Like when you have any experience or a chance to call like an OpenAI API, you're probably familiar with that API endpoint. And then after that is try to process your prompt, which is Vincent already mentioned like a paged attention, or which is like a prefill and decode, how to process and how to manage your key value cache kind of stuff. And then this is like a more throughput layer once you got your request. And the last thing is infrastructure layer, which is you can see that on the bottom. Like this is actually like the Kubernetes workers. And then some of the Kubernetes worker, like a bare metal, they attach their GPU accelerator, could be NVIDIA or Google or like AMD, Intel. So there are many kind of GPU accelerator based on your AI services. So sometimes your AI services maybe not require the big GPU process at all. Because you can ask, who is Vincent? And then pretty much a simple question, who is Daniel? Simple question. But if you ask a very complicated, high computational, like a reasoning thinking, asking would based on math, and then you probably big giant model. So this all kind of stuff. And then, so I'm not going to detail because Vincent already mentioned a lot of stuff here. So let's go jump into demo. So you probably will be going sleepy after lunch. So let's take a look at that. So of course, today is a cloud and container track. So this is a Kubernetes cluster, like based on Red Hat OpenShift, like a more enterprise-ready container platform. And I already deployed the Quen model here as a container using Kserve, which is like something like deploy your AI model as like a Knative, like a serverless. So, but you can also deploy AI model, just a general normal pod as well. And then here's just some like a router scheduler. It's like semantically, and then based on your prompt, and then based on allocated resources, kind of stuff. So your scheduler is not gonna guess anything. So based on your prompt, and then it automatically figure out which KV cache is available for this processing this prompt kind of stuff. And then here's one of the great things, these Kubernetes cluster based on OpenShift. And then, so I don't need to remember my password, by the way, really fast. Okay, and then this is more like a AI console, web UI. And then I have some project, and then when I go to, it's more like a formula with the data scientists, and now they have their own very fancy name, which is AI engineer. So go to, yeah. Everybody's saying AI. So I met a lot of AI engineer, and I asked them, what is your role and what do you do every single day as your daily job? Oh, I'm training a model for like a stupid model, make it smarter. And then sometimes I gotta create a Python AI app, just like that. Oh, you are a data scientist? Yeah, I love that job title more rather than AI engineer, because a data scientist is more like a scientific job. And you can see here's my Quen model. So, and also allocated GPU processor and running on like a VLLM kind of stuff. So when I go to here, and there are one other namespace, which is a project. I already deploy Prometheus and Grafana for observability, because as the like a cloud administrator or a DevOps engineer, they always wonder, how do we observe telemetry data from end user, could be human being like you guys, or some of the third-party application into your business application backend there, like a Java, .NET, Python, or database, among others. So now we are talking about AI. So as application standpoint, AI model just one of the resources. And then people are wondering how do we allocate these huge resources on like a workload or a payload on top of the AI models, and but also VLLM or LLMD kind of thing. So here's my graph on that kind of stuff. So I just gave it a try several times this morning, make sure everything is okay. I also prayed demo God. This is a live demo. And so as you can see, cache usage is 0 right now. And back to my application. And here's my, I have some kind of job here, like a, if I do, just I'm gonna show that thing. Here we go. So this is just like a Kubernetes job, very simple. And then we created like a multi-benchmark job from like a publicly available. Let me show you a little bit later. And I'm gonna just run that job directly. My remote OpenShift cluster is Kubernetes running on somewhere Amazon on United States. And then back to the here, and then back to the my demo project. And then the job is now starting. And I go to job, and then when I go to here, and then this is a randomly generated many stupid question parallelly. So this is like a benchmark testing stuff, and then asking like where is capital of France or where is the capital of Japan? Very stupid question. Everybody knows. You don't even need to ask a ChatGPT or AI model, but that's make it very heavy role. And then like maybe some another stupid question: who is more handsome between like Vincent and Daniel? So any kind of stuff. This is many questions coming up, and then when I go back to my pod, and then here is a kserve, and then the model thing, and then go to logs again. And then let's try to find like a decode. And then you can see that, go to under the last one. So this is actually Vincent mentioned earlier, like page attention. So when you ask as a prompt engineering, and then that coming through your AI model, like through the AI application, of course, and then this automatically LLMD try to find out, and VLLM as well. So where's so it's a preview, the process of your prompt, and then store your key value cache in advance. And then when you process actually that prompt question, and then it retrieved that cache store again. So whenever you got some similar or relevant question, it's actually using KB cache. That's why we got a kind of thing, and then go to VLLM. Oh, now we got some another number, and I'm not lying. This is not pre-recording. So you can see that here's a part automatically like a GPU cache usage is a keep real time rebalancing, and here's a coin server. We have actually two parts today as the demo. I'm not going to scale out this part like 100. Maybe my manager going to be kill me because, oh, you spent a lot of money one trip to Japan, like 10 grand. And I'm not going to do that. So just two part. It's a keep load balancing between, like you can see that here, like 37.9 and 36.7. It's a keep changing the number at the value load balancing based on prompt because you keep coming stupid question. But in reality, in production, so this is maybe a recommendation way on the Kubernetes. How do you scale out based on your prompt, more like a semantic routing or more logical thing like that. So one last thing is I want to show back to my topology. And then my job is done, but it still takes a little bit of time to balancing and processing from LLM. So a lot of people are actually after I showing this to them, hey Dan, so how do you set up this whole kind of LLMD kind of thing? And then it basically using like an operator. So we so there are many different ways how do you set up software kind of thing on Kubernetes. Like using Helm chart, or you can use operator, or you can actually do the like a more manual stuff. So there are, you can see that there are many operator kind of stuff, like a NVIDIA for GPU operator, and then node feature discovery operator, and OpenShift AI, and this, of course, service mesh, which is like a Envoy proxy load balancing in the between LLMD and the distribution kind of thing. All right, and then we're gonna wrap it up, and I'm gonna hand it over back to Vincent.
All right, thank you for the demo, Daniel. So let's do a bit of a recap, right? What have we discussed today? if you are looking at an enterprise AI blueprint, this is the way to look at things, right? Your pillar one, the foundation to manage infrastructure, very clear that Kubernetes is now the de facto project and stack to really handle the orchestration of accelerator hardware. It will be even more de facto as the complexity of accelerator actually increase, right? We see a lot of specialized accelerator coming to market. And so imagine as an engineer having to deal with the complexity of orchestration across this stack. Really, really complex. And so that's a good fungible GPU fabric. On top of that, you need to think about your engine. And the engine, what we've shown is projects like VLM really helping you to provide better throughput, better utilization of your hardware, specifically to inference. There's other benefits, obviously. Observability we've seen is another one. Once you start trying to understand what you can do to improve your optimization, very important to have standard telemetry coming in the process to understand why you're actually not hitting a cache, for example. And so VLM will provide you this kind of ability to understand at a low level how to start maximizing your limited resources. And the last bit is really the value stack, right? So I want to insist on this. LLMD is a pretty new project, but what is really important in LLMD is, you're probably not aware of the origin, but we spent almost a year and a half to 2 years before LLMD we came to market to think about the problem of how do we architect efficiency across the entire stack of AI. The reason was we saw a lot of open source projects, like Run AI from NVIDIA is an example, where you are giving me nice optimization, but only on the mixed slices. But because you have no awareness of the caching, of the request, of the semantic of it, you're actually taking a lot of dumb decisions, if I'm honest. So the problem that we saw is, how do we build an architecture that is actually aware of everything from like your resource management, your utilization, and then your dynamic allocation. LLMD today is the only project, the only open source project out on the market that gives you this SLO management across the entire set of layers of your AI architecture. It understands your GPU level management. It understands your caching, your inference optimization. It understands the performance of your model as well. And so that's a very important takeaway. So you are going to see this project a lot more, I expect, in the future. And really, it's very important to think about this because this is actually the layer that, from an AI application point of view, is going to be your orchestration and your abstraction layer for most of you guys who probably just want to build AI application and you don't really want to have to deal with GPU type of logic.